Welcome to Chapter 23, Part 2, Eddy Currents, Generators, and Back EMF. What exactly are eddy currents? Well, when a conducting material enters into a magnetic field, the magnetic field induces eddy currents. These are circular loops of current, just like when we had a circular loop or a loop of wire moving into or out of a magnetic field, it generated a current. So as this enters the magnetic field, it generates a current, and as it exits the magnetic field, it generates a current in the opposite direction. When it is actually fully immersed in the magnetic field, then there's no longer any change in the magnetic flux, right? So the magnetic flux change with respect to time at that point is zero. So no magnetic field or no eddy currents when it's fully immersed in the magnetic field. So there are currents when it comes in, currents when it comes out. These currents oppose the change in flux. So as this comes in, it induces a magnetic field that opposes the one that it's moving into. What does that mean? This essentially becomes for a moment a dipole or a magnet with its north pole towards the south pole of the magnetic field that it's moving into. This causes there to be a braking effect as these two poles exert force on each other. This magnetic braking happens when you swing into, in this case, into the field. And what you would see is the velocity of this quickly go down. Now, this doesn't have to be a magnetic material, it only has to be a conducting material. If you want to see this in a YouTube video, just follow the link down here and you'll see a great example of this flux happening, or of this magnetic braking happening. Things that can be done to reduce the effect of eddy currents mostly include things like you see here, where the conducting material has been divided up into tines or fins or into veins, and so that the currents that get induced are not as large and they don't cover as large an area. You might think you've never experienced this, but if you've ever ridden a roller coaster, you probably have. Most modern roller coasters use rare earth magnets at the end in order to perform magnetic braking. This allows braking to happen without the roller coaster having to actually touch any other part of the structure. We look before at generators and a generator that generates a sine wave output. So let's look at this a little more closely. In the figure here, we have a loop, and we're going to pretend that it's a circular loop instead of the square one we see here. We have a circular loop, and in just 60 milliseconds we go from being parallel with the surface vector, parallel to the magnetic field, to the surface vector being perpendicular to the magnetic field. Remember, the surface vector is perpendicular to the actual surface. So let's suppose that this is a circular loop with a radius of 5 centimeters and it has 200 turns, and it's in a 1.5 Tesla magnetic field. Again, it goes through a quarter of a turn in 15 milliseconds. That means it goes through a whole turn or a whole rotation in 60 milliseconds. We know from Faraday's law that the induced EMF is minus n times delta phi b over delta t. And we have n equals 200 and delta t equals 15 milliseconds. Well, we also know that 5b is the B field strength times the area of the loop times the cosine of theta. So delta phi b is the delta of BA cosine theta. Well, the B field and the area don't change, so this can be written as BA times delta cosine theta. Since theta goes from 0 to 90 degrees, delta cosine theta is just cosine of 90 degrees minus cosine of 0 degrees, which is minus 1. If we put this back in, we get delta phi B is minus BA. This makes the EMF equal to NBA over delta T. Now with N equals 200, B equals 1.5 Tesla, delta T equals 15 milliseconds, and A equals to pi onto 0.05 squared meter squared, which is 7.85 times 10 to the minus third meter squared, we get a total EMF here of 131 volts. Now if you remember from our last lecture that the top and bottom of the loop do not contribute to the EMF, and the EMF due to one side is BLV sine theta, the sine theta takes into account the component of velocity perpendicular to the B field. Now since there are two sides in this problem, the total EMF is 2BLV sine theta. From rotational kinematics, this omega rotational velocity is V over R, so V equals omega R equals omega times W over 2, since R is the width of this loop over 2. And the angle in a uniformly rotating system as a function of time is theta equals omega T. Right? Omega is the rotational velocity, T is time, so omega T gives us how far around we've rotated. If we substitute these back into the EMF equation, we get that the EMF is the length times the width times B times omega times sine omega T. Well, the length times the width is just the area, so the EMF for in loops is NAB omega sine omega T. This is the instantaneous EMF that occurs as you rotate through. You also remember from our rotational kinematics, omega equals 2 pi f, or 2 pi times the frequency, or 2 pi divided by the period. We now have a peak EMF. E naught is NBA omega. So the instantaneous EMF looks something like the sine wave here, where it goes up, down, right? And that is one period. There's another concept that we want to introduce here that I will explain better using a problem later. But when you run a motor, you also force it to be a generator, which creates an EMF opposing the one you're using to run it. And when I create the video for this problem, you'll be able to see better exactly how this affects the use of motors. Until next time, I'll talk to you later.